To operate modern integrated photonics, systems handling everything from high-density data storage to ultra-fast optical switching, engineering teams rely on materials capable of altering light based entirely on the intensity of the light itself. This specific capability is the domain of nonlinear optics. For decades, the industry standard relied heavily on naturally occurring or bulk-grown inorganic crystals like beta-barium borate, quartz, and lithium niobate. These inorganic nonlinear optical materials are widely deployed today, driving extreme-scale applications like second harmonic generation used to increase gravitational wave detector sensitivity. But inorganic crystals present rigid physical limitations. They inherently possess small nonlinear optical coefficients, and they offer very little structural diversity. You cannot easily tweak the atomic structure of a quartz crystal. That rigidity creates a severe bottleneck when engineers attempt to design the architecture for higher speed and higher density optical data processing. To advance these systems, the field is moving away from rigid inorganic structures, turning to new materials where optical properties are precisely engineered at the atomic level. Organic molecules offer a highly tunable alternative. When compared to their inorganic counterparts, these organic systems yield vastly higher polarizability and operate with much faster response times. By synthesizing organic molecules with specific geometric asymmetries, researchers dictate exactly how a material absorbs, refracts, and manipulates an incoming electromagnetic field. These complex macroscopic optical behaviors, like advanced signal routing and frequency mixing, are directly controlled by this microstructural chemical tuning. Engineers target specific nonlinear metrics through this chemistry, focusing heavily on maximizing polarizability and achieving a highly tunable nonlinear refractive index. Modern optical engineering now centers on chemical synthesis, shifting focus from finding naturally occurring crystals to building bespoke molecular architectures. The engine driving this organic nonlinear optical activity is the push-pull molecular system, the donor-pi acceptor architecture. In this model, an electron donating and an electron accepting group are positioned at opposite ends of the molecule, connected by a continuous carbon bridge holding a delocalized pi electron cloud. This push-pull architecture forces the material to be noncentrosymmetric. The electron density naturally leans heavily toward the acceptor group, creating a permanent resting asymmetry in the charge distribution. When an intense external electromagnetic field, like a laser pulse, interacts with this molecule, it triggers a process called intramolecular charge transfer. Because these pi electrons are highly diffuse and loosely bound to their nuclei, the external optical field easily displaces them, causing the electron cloud to oscillate violently along the bridge without breaking the molecular bonds. This massive, rapid displacement of charge generates a secondary, modified optical field. In chemical terms, this extreme responsiveness is measured as high first-order hyperpolarizability. The continuous pi bridge acts as a highly conductive track. By building asymmetry into the ends of that track, chemists translate structural geometry directly into extreme optical nonlinearity. To see how minute, localized structural changes radically alter this hyperpolarizability, we can look at a natural case study. These are the porphyrin ring structures of two photosynthetic pigments, chlorophyll A and chlorophyll B. Their conjugated system skeletons are nearly identical. There is exactly one chemical difference between the two. Chlorophyll A features an electron-donating methyl group attached to the ring. Chlorophyll B, however, features an electron-withdrawing aldehyde group in that exact same position. This single substitution changes the internal charge dynamics. The electron-withdrawing aldehyde group pulls the pi band towards its oxygen atom, creating a massive dipole moment and making chlorophyll B highly polar. Researchers tested both of these pigments using degenerate four-wave mixing, a technique used to measure optical nonlinearity in solutions. This chart shows the absolute value of the third-order nonlinear optical susceptibility for both molecules. Because chlorophyll A utilizes an electron-donating group rather than a highly polar electron-withdrawing group, its susceptibility is roughly 3 times higher than chlorophyll B. Swapping one functional group on a massive porphyrin ring completely rewires the molecule's internal polarity, dictating the magnitude of its macroscopic nonlinear optical response. Precise structural tuning dictates the magnitude of susceptibility, while also offering the ability to invert the physical nature of the optical response itself. We see this clearly in Schiff bases, a highly tunable class of third-order nonlinear materials, characterized by their azomethane or carbon-nitrogen double bond groups. To measure their properties, researchers pass a laser through the molecules using a Z-scan technique, accurately extracting both the nonlinear refractive index and the nonlinear absorption coefficients. This line graph plots Z-scan data for an asymmetrical Schiff base, compound L2. The curve traces a distinct peak-to-valley waveform. In physics, this peak-then-valley shape proves a self-focusing effect is occurring. The material possesses a positive nonlinear refractive index. Now consider compound L3, a different Schiff base containing a nitrogen dioxide group. Unlike L2, L3 is synthesized to be highly symmetrical. When we overlay the Z-scan data for L3, the waveform is perfectly inverted, dropping into a valley before rising to a peak. This inverted curve indicates that the symmetrical L3 compound possesses a negative nonlinear refractive index and exhibits saturable absorption. The physical mechanism causing this inversion comes down to spatial geometry. Changing the mutual orientation of the aromatic rings from an extended conformation to a parallel conformation reverses the optical behavior of the molecules. By manipulating a molecule's spatial symmetry, chemists achieve absolute control over the sign of its nonlinear refractive index. This exact degree of molecular control is required to construct the hardware for modern all-optical data networks. An ultra-fast optical switch operates by routing data without converting it to electricity. To do that, it requires a material where the refractive index changes instantly with fluctuations in light intensity. Highly asymmetrical donor pi acceptor systems with extended pi bridges fulfill this requirement perfectly, providing the massive third-order nonlinear responses needed to instantly bend the light. Conversely, systems require optical limiters. These components protect sensitive optical data storage drives and photodetectors from irreversible laser damage. Materials exhibiting strong two-photon absorption, or saturable absorption, exactly like the symmetrical Schiff base L3, act as ideal optical limiters. These chemical structures effectively cap optical transmission. They absorb dangerous, high-intensity energy spikes while remaining entirely transparent to normal, low-intensity data streams. Synthesizing organic thin films with bespoke, tunable nonlinear coefficients is the crucial link connecting molecular chemistry to functional, real-world photonics. Historically, controlling the flow of intense light relied entirely on the rigid, unyielding physics of naturally occurring or bulk-grown inorganic crystals. Future photonic systems bypass these geological constraints by utilizing the structural flexibility inherent in organic chemistry. We are bridging the gap from manipulating the quantum mechanics of a single, delocalized pi bond to operating a macroscopic telecommunication switch. Understanding molecular symmetry and electron density is no longer an exercise confined to chemistry labs. It is the fundamental blueprint for building next-generation optical networks. By engineering the exact geometry of the molecule, we dictate the behavior of the light it encounters.